extension of what we just last did. Intervals of increase, decrease, and your critical numbers. The only difference is I'm not doing polynomials. It's going to be something else. So, let's try this one out first. F of x equals, quiet please, sine x, because everyone loves trig, plus cos x from 0 to 2 pi. Okay. Hey guys. We're writing these out because these take so much that if I just type, I end up printing pages that cost 10 cents a page, plus the paper to have one equation and another equation down here, and it's such a waste of printing. So I'm not doing it. So this unit I don't print. And then eventually what we'll do is I'll give you one equation, and then I'm going to ask you for the intervals of increase, decrease, the critical numbers, the max and mins, the second derivatives, the concavity, and the critical numbers of that, which is about a page and a half. This is nuts. Yes. All right. So I want the critical numbers of the first derivative. Where do the critical numbers of the first derivative happen? When the first derivative equals what? 0. Why? First derivative, yes, this first derivative represents the tangent slope, and the critical numbers are equal to 0 at where? Where are the tangent slopes equal to 0? Max, mins, points of inflection. Remember when we talked about that? We talked about when we looked at a graph like this. This has tangent slopes that are what? Positive. This is tangent slopes that are what? Negative. And this is tangent slope that is 0. So that's why we're finding the critical numbers of the first derivative, because that gives us our max or min and points of inflection. It's sometimes critical numbers can sometimes also result in asymptotes and stuff like that, depending on if you have restricted variables and stuff like that, which you would have if I gave you a rational, which you will get. Just not at the moment. So our first step is to get the first derivative. So f prime of x equals, what is the derivative of sine? Cos. And then, what's the derivative of cos? Negative sine. And in order to get the critical numbers, what do we have to do? We need to set f prime of x, or the first derivative, or the tangent slope equal to 0, right? Because we're trying to find all those spots where the tangent slopes are equal to 0, the x values where that's happening. So to find out where the x values of the tangent are equal to 0, we set the tangent equal to 0. So we get 0 equals cos x minus sine x. Now, I can move the sine x over, so I have sine x equaling cos x. Do you agree? Now, there's two ways we can do this. We can do it just the way it is. Where is sine x equal to cos x? That's a 45, right? At pi over, when it's root 2 over 2 and root 2 over 2. Or negative root 2 over root 2 and root 2 negative root 2 over 2. Oh my gosh. Or we can actually divide the cos over and get this side equal to 1. So I can divide cos x over. What's cos x divided by cos x? 1. So I want where tan x equals 1. And where does that happen? At 45. Where is it positive 1 at? Quadrant 1. Thank you. There we go. And quadrant what? And why is that? Y is equal to 1 because tan is when sine and cos divide each other and get back. Well, the coordinate here is root 2 over 2 and root 2 over 2. When I divide those, I get positive 1. The coordinate here is negative root 2 over 2 and negative root 2 over 2. When I divide those, I get positive 1, right? The other two quadrants, you would result in negative 1 at. Yes? Do you know what I mean? I subtracted the sign x over, and then I divided the cos x over here. All right. Quiet, please. So in radians, where does this happen? Pi over 4, and where? What is this one? Pi over 4. And those are the only two answers I'm going to give. Why? You add pi to it. And you want it between 0 and 2 pi. We want only the answers between 0 and 2 pi, and those are the only two places where tan x will come out as positive 1. So those are going to be my critical numbers. Now, my domain is restricted. Every domain we've done so far is from negative infinity to positive infinity because we have not had a restricted domain, and we've been dealing with polynomials, correct? So when I go to do the number line of this one, I'm going to actually have closed endpoints because this is equal to 0 and 2 pi and inclusive. So I'm going to go 2 pi here and 0. And in between, I have pi over 4 and 5 pi over 4. So to find out where it increases or decreases, we are going to plug it back into the equation that's equal to 0, correct? So we actually have to do test points and plug them into this. Okay? So my one test point I can do, what's below pi over 4? Well, I can run a pi over 6. What falls between pi over 4 and 5 pi over 4? Pi. And then I can do 3 pi over 2. So you're going to do your test points. You're going to do f prime of pi over 6. And we're going to get cos of pi over 6 minus sine of pi over 6. Put your calculator in radian mode. Should always be in radian mode in calculus if you don't use degrees. And you're going to go cos of pi over 6 minus sine of pi over 6. Twice the other multiple. It's going to be a crazy thing. We're going to try it out. Okay, cos of pi over 6 minus sine of pi over 6. Do I actually care what the answer is? No, what do I care about? The sign. What is the answer, positive or negative? Okay. And I'm going to do f prime of pi. So now I have cos of pi minus sine of pi. This one you shouldn't need your calculator for. Cos of pi is -1, sine of pi is 0. So it's going to be negative. Please don't go, oh, it's positive, negative, it's going to be positive. That's not always the case. You can end up with a point of inflection in there, right? Which would be negative to negative or positive. But you have to find them all out. And then the other one is 3 pi over 2. F prime of 3 pi over 2 is at 270. So I need cos of 3 pi over 2, which is 0. Minus sine of 3 pi over 2, which is -1. So minusing a -1, which is positive. So is this a ton harder than what we did before? No. You just have to realize you can get into tan, right? Now, I can do the intervals of increase. So I have my critical numbers. My critical numbers are at x equals pi over 4 and 5 pi over 4. See why I don't print the notes? It takes the whole page halfway, and then usually print it equation. I would have literally f of x equals sine x plus cos x in that, and it costs the school money. So I'm not doing it. That would be all that's on one page. All right. Now, intervals of increase. Intervals of increase are from, now 0, is it square or round? Don't fault what I wrote, except for reason. It's square, because it's equal to 0, right? That's why I have a closed dot on the end here. So the intervals of increase are actually 0 to pi over 4 round bracket, union 5 pi over 4 to 2 pi square bracket. Intervals of decrease is from pi over 4 to 5 pi over 4. Why are these rounded? Is it decreasing at pi over 4 and 5 pi over 4? Because if I made them square, then I would be saying it's decreasing at those values. Is it decreasing at those values? No, those values are max mins or points of inflection, correct? All right. So I am doing what on, so pi over 4 is either a max or a min or a point of inflection. It could be an asymptote, but because this doesn't have any NPDs, it's not an asymptote. So it's max, min, or a point of inflection. So we are doing what on the opposite side of, what are we doing on the left of pi over 4? Increasing. What are we doing on the right? So what is pi over 4? It's a max, and we'll deal with what the y is in a second. 5 pi over 4, what's it doing on the left? Decreasing. What's it doing on the right? So what is it here at 5 pi over 4? A min. So we need to find out where the max and min are. So we have a maximum at pi over 4 and some sort of y. We have a minimum at 5 pi over 4 and some sort of y. Is that an agreement? How do we find the y? Do we plug it into the first derivative or the original? Y. That's correct, for y. We're finding the max and the min on the what? On the original, right? So we're finding the max and the min on the original. We have to plug them back into the original to get the y value that goes with it, not the first derivative. So we are going to find f of pi over 4, not f prime, f of pi over 4 equals sine of pi over 4 plus cos of pi over 4. They're easy because they are both root 2 over 2 and root 2 over 2. So you get root 2 over 2 plus root 2 over 2. Most people can get to this, and then I get some crazy mathematics happening. We have a common denominator, which is good. So we can put them all over 2. Now, what is 1 root 2 plus another root 2? 2 root 2s. You know what I get? Let's just say it's 2. You multiply it, even though there's a plus sign. So it's crazy. Root 2 times root 2. No, it's a plus sign. 1 root 2 plus 1 root 2 is 2 root 2s. And then what can I do? So what's my answer? So this one is a maximum of pi over 4 and root 2. Then I have to do 5 pi over 4. So I'm going to get sine, oh my gosh, sine of 5 pi over 4 plus cos of 5 pi over 4. Struggling. What is sine of 5 pi over 4? Calgary Stampede. Negative root 2 over 2, negative root 2 over 2. So it's minus root 2 over 2, minus root plus neg, oh my gosh, plus negative root 2 over 2, which is negative 2 root 2 over 2, which is negative root 2. Yes, there's a lot of 2's. So is it horrifically hard?
Yes.
No. It's just a little bit different. That's what it is. They're all long. Yeah.
For every question, we always have to find the line. Like, we're gonna have to.
If I ask for max and mins, yes. I'll ask for coordinates max and mins. But if I don't, then you can do a coordinate max and min. It's fine. Okay. New question. Trig is fun, okay? Trig is fun, okay? F of x equals, you know what else is fun?
No.
Radicals. Awesome. Square root 6 minus x. Do you know what's even more awesome? That half of you don't know those are called radicals. You like ebb and flow between radicals and radicals. Radicals. Full stop with an R. I don't know. Radicals have a radical sign. Because they're really radical. Like that. And radicals are the fractioning things. The fractioning things are very good. Yeah. Okay, friends. I told you we're all going to pay attention because if you pay attention, this question is easy and you can replicate it and you're totally fine. If you don't pay attention, you will be lost, little souls. We don't want you lost, little souls. Okay? I told you that the very first thing we have to do before we look for critical numbers, before we look for increasing, decreasing, before we look for max and mins, is what? Domain. The last one gave us the domains. We didn't have to really do much, correct? This one, we have to find the domain. Now, everyone type that into their calculator so you can see what it even looks like. X square root 6 minus x. Type it in your calculator. Good listen. All right. Does the graph in front of your face have a domain of XER? No. What do we know about radicals? Since you were little, what's your rule? It has to be greater than or equal to 0, because we can take the square root of 0. Yes? What's the square root of 0? 0. What's the square root of -1? Can't do it. So when people are like, I don't know if we can take the square root, everyone will always say, you can't, it has to be a positive number. Well, it's not just a positive number, it can be 0, right? Just be greater than or equal to 0. So let's take what's underneath this radical. Everyone's paying attention, so I'm not leaving them. If you're on your phone, you're not paying attention. It's impossible. It's not a challenge either. Okay, so what's under the square root, we know has to be 0 or a positive number. Is that not true? So I'm going to take what's under the square root. I'm going to say 6 minus x has to be what? Greater than or equal to 0. Now you can do this one of two ways. You can move the 6 and then divide by -1, but then you're going to be dividing by a negative, and you have to remember to flip your inequality sign, because that's what happens. The only difference between solving with an equal sign and solving an inequality is if you divide by a negative, the inequality sign flips. That's it, right? So you can do that and then hope you remember to flip it, or you can do this. It's crazy. Now, I get people real confused when the x is not on the on the left-hand side. You're like, you had me, and then now you put it on the right-hand side, and I may have gotten a 90-something in 30-1, but I can't do this. And yes, you can. All you have to do, are you paying attention? Is you take the symbol with the variable. So you don't like it on the right? Cool. Put it on the left. I have an x. I have a 6. The way the variable is shaped towards the actual, the way the symbol is shaped towards the variable has to stay the same. Okay? So if this is closed to the x currently, do you see that? It's pointing towards the x. It has to point towards the x still. That's it. You can move your variable around, right? your symbol, the inequality symbol, just has to look the same. So if x is closed, it's pointing towards the x, and it's pointing towards the x. So what is our actual domain? X is less than or equal to 6, correct? And some people are like, I like it when it's on the left because then it makes an L, and L means less than, and then that's my teacher remember it with an L, and then you move to a variable to the other side and ruin my life. Well, you can move it to the other. You can do it. I believe in you. Okay, just move it. So we need to make a number line. Our number line no longer is from negative infinity to positive infinity. It's not closed off from 0 to 2 pi. This one is less than or equal to 6. So if I draw myself a number line, where is the 6? On the left or on the right? It's on the right. Is it a closed dot or opened dot? Closed or open? We have all the answers for 2 of them, and at the end of okay. Closed because it's equal to 6. Is there anything stopping this end? No. This end is still negative infinity. We agree? Everyone's following along? So at the very least right now, we have ourselves the number line where it's going to be. So now we have to get our critical numbers. How do we get our critical numbers of the first derivative? Well, we first have to get the, and we've set it equal to. Okay, you try it. Get the first derivative of that. How are you going to have to do that? Starts with P, rhymes with product rule. Product. Let's look at this. So we get f prime of x. So we have f, we have g. G would be the same as 6 minus x to the half. F prime is 1. G prime is a half. 6 minus x to the negative a half times negative 1. Negative a half. 6 minus x to the negative a half. Whatever. Okay. It's because this thing's wearing off, but you can replace it. So. All right. We have done nothing. We just told what those things are. So, ready? So you get G. And this is where I said if you can't do derivatives. Remember what I told you in the last unit? If you can't do derivatives and you can't take out GCFs, this unit is impossible. Because if you can't differentiate this and take out your GCFs and get your critical numbers, you can't do any of the questions. Right? So polynomials are easy. It's when we get to these other advanced ones. So we have G times F prime, which is 1, plus F, which is a half, negative a half, sorry. 6 minus x to the negative a half. G prime times x. So what can I take out of these? Yes. All right. We're going to take out a negative a half. Paying attention. You can take a negative a half out, and you can take out what? 6 minus x to the negative a half, which is why I drilled this into your head so bad. All right. First term. If I take a negative a half out of 1, what am I left with? I took a negative a half out. Negative 2. You could take out a positive. Did you take out a positive half? And then I'll just stick with what you did. Okay. Okay, 2. And then take a negative half out of 6 minus x to the half. I'm just left with 6 minus x, which has to be just 2 distributed in. Stop it. Then I took a negative half out, I took that out, I'm left with a plus x. We agree? Everyone's following along? Not been anything different than what we did last unit. So, the 2 can drop to the denominator. The 6 minus x to the positive a half can drop to the denominator. And then I get 12 minus 2x plus x. 12 minus 2x plus x. And so I get 12 minus x over 2 bracket 6 minus x to the half. Now, some people will say, Mrs. Lepp, that's in the denominator, so that's an asymptote. True, an asymptote on the first derivative, correct? It is not an asymptote on the original. Why is it not an asymptote on the original? The original is a radical graph. Radical graphs don't have asymptotes. That's the hugest hint. Like, you can't have an asymptote, it's a radical, right? So even if it comes from the denominator, these are all critical numbers, no matter where it comes from. Critical numbers of the first of the original. So I take each of these separately and set them equal to 0. What's the matter? Why are you all giving me this face? Yeah. Pardon?
No, like the one right.
Oh, this is the negative x. I don't know what yours, so this is the negative.
No, right there, like, if it's like g first, the degree is g, like f and g, like product rule.
Yeah.
Like, you know the g right there?
Yeah. Negative 1? I did it. I have a negative 1 behind it. The derivative of 6 minus x is negative 1. All right. So, in the top, that's an eraser. In the top, we can take out a 3 and we'd be left with 4 minus x. The bottom we have a 2 and a 6 minus x to the half. I just GCF to 3x, right? If you don't GCF a 3 out, will you get the same answer if you set it equal to 0 and solve? Yes. So it's not a big deal. You could take the 12 minus 3x, set it equal to 0, and you'll still get the same answer as b, which is 4. Okay? So we have two things that are variables. We're going to have 4 minus x equals 0. 4 equals x is one of my critical numbers. And then I have 6 minus x to the half equals 0, which really doesn't matter because to get rid of a half, I raise the power of 2 over 1. And 0 to the 2 is 0. So it doesn't matter that there's a half there. Move my x over, 6 equals x. So that's another critical number. 6 is a critical number. How do you get rid of the half? You times it by 2? What? I just took this and set it equal to 0. That's a variable.
I got you.
So it doesn't matter if it's numerators or denominators, it results in critical numbers. So 6 is a critical number. It can't be literally a max or a min because it's the end point, right? It's where the graph ends. The only thing we sit in here is a 4. And then we have to plug test points into this. So I can plug in a 0 and a 5. Because 4 is my critical number. It goes between negative infinity and 6. And 6 is already on my number line. I have picked values that fall between them. So I'm going to get 3 times 4 minus 0 over 2 and 6 minus 0 to the half. You take the square root of any positive, you get a positive. So this is going to be a positive times a positive over a positive times a positive, which results in a positive. Then I plug in the 5. 3, 4 minus 5 over 2 times 6 minus 5 to the half. It's going to be a positive. 4 minus 5 is a negative. Multiply those. Positive and a positive. So it's a negative over a positive, which is a negative. Now go press graph. Go back to your calculator. Look at your calculator. Is there a maximum at 4? Go second trace max. left bound, right bound, enter. You should have a maximum at 4. On the left of 4 to infinity, is it decreasing or is it increasing? It's increasing, and what is it doing between 6 and 4? It's decreasing. Look at your actual graph of your calculator, right? It's going like this. It's going up to that maximum of 4 and whatever it is, and then down to 6. So you found the things that it actually is. Now, could I stick to polynomials and you guys would find this unit really easy? Sure. Would it make my life easier? Yes. Would you be pooch next year? Yes, you would. So I'm not allowing you to be destroyed next year. Will your test have a lot of polynomials over everything else? Sure. Will it still have some of these? Yes. Okay, you're trying this one on your own. So we have to first come up with our domain. X plus 3 has to be greater than or equal to 0. So x has to be greater than or equal to -3. Close dot on -3 greater than or equal to gives me infinity. All right. Then I have f, which is x, f prime, which is 1, g, which is x plus 3 to the half, and g prime, which is 1/2 x plus 3 to the -1/2. F prime of x equals f times g prime plus g times f prime. So we can take the half out. We can take the x plus 3 to the -1/2 out. And then when we take the half out, we're left with the x, and the half is gone, so it's just an x. Plus, take a half out of 1 and left with a 2. X plus 3 to the half divided by x plus 3 to the -1/2 is just x plus 3. Now, some people don't want to move that to the bottom. You don't have to. It's just easier when you're actually doing the timeline or the number line if it is. So I'm going to move it down. You don't have to. So I have 2 x plus 3 to the half. Here I have 2x plus 6. So I'm going to end up with 3x plus 6, which can reduce to 3x plus 2 over 2x plus 3 to the half. So my critical numbers come from x plus 2 equals 0, x equals -2. And then I have x plus 3 to the half equals 0. To get rid of an exponent of a half, I raise it to a 2, because a half times 2 is 1. But this is a 2. It doesn't matter what that is. If you use 0 to any exponent, it's going to go away, correct? So it's going to be x plus 3 equals 0, x equals -3, and it really doesn't matter because that is an endpoint. Okay, then we plug in our test points. I'm going to plug in -2.5. So I'm going to go 3 times -2.5 plus 2 over 2 times -2.5 plus 3 to the half. So I'm going to get positive times a negative over a positive times a positive, which is a negative. Then here I can plug in 0. So I can go f prime of 0 equals 3, 0 plus 2 over 2, 0 plus 3 to the half. So I'm going to get a positive times a positive over a positive times a positive, which is a positive. So we're decreasing between -3 and 2, close bracket on the -3. We're increasing between -2 and infinity. What's happening at 2? It is decreasing to increasing, and it's not drawing. So this is a min, right? We agree? All right. So tomorrow we're going to go over a rational one. So we're going to get some asymptotes. And then we're going to go over how to do this if I give you restricted domain as well. Okay, that's what tomorrow is going to be. Then we move on to second derivatives, concavity, and the second derivative test to find out if it's master.